Let's learn about Cartesian vectors and how we add and subtract them. So we're going to move into three-dimensional vectors in a Cartesian coordinate system, learn how to find the magnitude and angles of the vector, and learn how to add them in 3D space. Now, the various items that we will go through today, normally we'd go through a reading quiz, but you probably haven't read it, so I would recommend that you go through that quiz after this lecture, perhaps after perusing the text. We'll talk about applications and how what we're studying is relevant to the real world. We'll talk about unit vectors, 3D vector terms, how to add these vectors, and then we'll have some examples and possibly a concept quiz and an attention quiz that we will talk through. So skipping the reading quiz, at least for now, let's look at applications for 3D force vectors. There are many machines and many structures that involve three-dimensional space. So some mechanisms you can simplify down to 2 dimensions, but many require 3 full dimensions in order to analyze them and understand what's going on in them. So in this particular case, we've got a power pole and it has wires that help support it, and those forces in those wires have three-dimensional components. They're not just in a plane. Now you could come up with a plane that represents any one of these vectors, or that contains, in fact, there's an infinite number of planes that contain each of these vectors. However, naturally, we want to analyze this in 3 dimensions because the entire problem or the entire system involves all 3 dimensions. So how could we represent the forces in these cables using all 3 dimensions, using a Cartesian vector form? Another application is where you have a radio tower, and radio towers are supported by wires pulling down on them, pulling them into the ground in order to prevent the wind from toppling them. Usually connected at essentially a point at the bottom of the tower, O in this example, and there are 3 separate wires shown here. How would we determine the resultant of all those forces from those 3 wires acting at the top of the cable? Why would we care? Well, we don't want so much force that the tower collapses, right? We wanted these cables to hold up the tower, not to make it collapse. But then also, as the wind blows, the amount of force in the various cables will vary, but we're just interested in figuring out the resultant, because obviously if the resultant of these 3 has a horizontal component, then the tower is going to topple. We need the horizontal components to all be balanced, and the sum, the resultant, to only have a vertical component. Now, it's really important to understand that we're dealing with right-handed coordinate systems. If you take your hands and you orient your thumb, index, and middle fingers in a way that kind of looks like you're throwing gang signs, but that has 90-degree angles between each of them, you'll notice that you've got a mirror image. The right and the left are different. There's no way to rotate your hands so that one finger points in the same direction. You'll always have a finger pointing in the opposite direction, no matter how you orient them. So we use right-handed coordinate systems. The way to understand that is you could point your hand in the direction of the x-axis, try to do it with me, and then turn your fingers through the smallest angle to get to the y-axis, and your thumb will point, and make sure your thumb points in a consistent direction throughout the rotation. Your thumb will point in the z direction. So it's x into y. If you take y, point your hand in the direction of the y-axis, and rotate it into the z-axis, your thumb will point along the positive x-axis. Similarly, if you rotate z into x, you'll get the positive y-axis. But anyway, we're interested in unit vectors, vectors that only have a magnitude of 1 and really only indicate a direction. So if we have a general vector A with some magnitude of A, then we could take the ratio of the vector to the magnitude, and that would give us a vector that has unit length. So, and would essentially be something that only points, that only has direction. An interesting thing about unit vectors is that they are dimensionless. They don't have any units, because if you think about it, if A is a force and we divide A as a vector by its magnitude, then the units would cancel, and so the unit vector would be dimensionless. Now, of course, that vector would point in the same direction as the original vector A pointed. The unit vectors in the Cartesian coordinate system are I, j, and k, and they go respectively with the x, y, and z axis. So I is along the positive x-axis, j is along the positive y, k is along the positive z-axis. Now let's think about a vector A. It happens to have its tail at the origin, but that's not absolutely necessary. And we've got a length along the x-axis of this vector A, or a projection of A onto the x-axis, a shadow if you will, equal to length AX. And then the shadow, if you will, of vector A onto the y-axis is AY, and onto the z-axis is AZ. So that's, if it's a position vector or a length vector, then those would be the various lengths along these axes. Now this vector can be written as the length along the x-axis in the I direction plus the length along the y-axis in the j direction plus the length along the z-axis in the k direction, and all of these have units of meters. Now the projection of the vector itself onto the xy plane is what we will call A prime. It's often very useful to imagine projecting the vector onto a plane to then later take that projection and break it down into its two-dimensional components on the x and y axis. And so then we could find the magnitude of A prime pretty easily. It would simply be ax squared plus ay squared square root. It's just a right triangle, so we use Pythagorean's theorem to find its length. Or we might use sines or cosines, whatever the case may be. I guess it would probably be a cosine in this case, to project A onto A prime and find the magnitude of A prime that way. So the magnitude of the position vector A, the original vector itself that's shown in sort of a teal color there, could simply be calculated as the square root of the sum of the squares of its lengths, ax squared plus ay squared plus az squared, and then square root. So another way to look at this is the length is a prime squared plus az squared, but we know that a prime squared is ax squared plus ay squared. This is more a proof to show you that we can extend Pythagorean's theorem into 3 dimensions beyond just 2. All right, now there's another concept with these 3-dimensional vectors that is important. That is the angle that the vector makes with respect to the coordinate axes. So you'll notice that vector A has an angle from the x-axis of alpha. It's kind of hard to see there in the figure, but it's there. It has a different angle to the y-axis beta, and then it has an angle from the vector to the z-axis of gamma. So we've got alpha, beta, and gamma that match with x, y, and z. Those are the directions of this Cartesian vector. So this is the orientation of it, if you will. Okay. So the value of these angles will always range from 0 to 180 degrees, because if you go past that, you may as well measure it in the other direction. Now, if we think about it and use trigonometry, we can realize that the cosine of alpha is ax over a. Now, look at the figure and this will make more sense. The vector A is just a length vector. It's the easiest one to think of. Of course, this would work with force vectors too, where the magnitude is the magnitude of the force. It's not really a length. But for a position vector, this is easy to understand. The length of the vector is A. If we take the length of the vector A over the projection of that vector AX, well, then we've got a cosine relationship, don't we? In fact, it would be the cosine of the coordinate angle alpha that would relate to the ratio ax over a. And it's similar for the other coordinate axes as well, with their respective angles beta and gamma for y and z. Now, it's really important to understand that these 3 angles, alpha, beta, and gamma, are not independent. Now, how is it that they have to satisfy this relation? Well, think with me for a minute. Cosine of alpha equals ax over a, right? That's what we've already discovered. So if we square both sides of that equation, we'd have cosine squared of alpha equals ax squared over a squared. Okay, well, we could do that for the other 2 directions as well, right? And so what we'd be doing if we add this cosine square of alpha to cosine squared of beta and so on and so forth, we'd be adding ax squared over a squared plus ay squared over a squared plus az squared over a. Now, or a squared, excuse me. So they have a common denominator. It is just a squared. All right. Well, ax squared plus ay squared plus az squared is exactly a squared. So we'd have a squared over a squared, which is 1, and that's why these angles are not independent. The squares of the cosines of the angle have to come up to 1. Now we can also derive this result from the definition of the coordinate angles in a unit vector. So what you see here is that the unit vector that points in the direction of A is the vector A itself divided by its magnitude A. And so we have ax over A in the I direction, ay over A in the j or the y direction, az over A in the k or the z direction. And if you think about ax over A is just cosine of alpha. So we could substitute that in for the I component, substituting cosine of beta for the j component and cosine of gamma for the k component. And one thing we know about the unit vector is it has length 1, right? So cosine alpha squared plus cosine beta squared plus cosine of gamma squared must be 1 squared, which is simply 1. All right, so let's talk about how we would add these three-dimensional Cartesian vectors. It's pretty easy. It's very similar to 2D vectors. All we have to do is add the components. So first of all, if we have vectors that we want to add or subtract, we've got to have them in component form so that we can work with them. So a force can be written in its x, y, and z components. And then if we have a vector A that is axi plus ayj plus azk, and similar for a vector B, then to add them, all we have to do is add ax plus bx, ay plus by, az plus bc, and then those go with the respective coordinate directions ij and k. So in other words, or I should say alternately, if we want to subtract b from a, then we need to take the negative of vector b, in other words, multiply through by a negative sign, and that will affect all three of the terms, and then add. So ax minus bxi plus ay minus byj plus az minus bzk. So adding and subtracting three-dimensional vectors is very similar to two-dimensional vectors. It's just that we've got a k direction now to play with as well. There are some important notes here, okay? Sometimes a three-dimensional vector will be given as magnitude and the coordinate direction angles, or it might be given as magnitude and projection angles instead. You should be able to use both of these ways of describing the vector and be able to change into a Cartesian form. So for example, a force vector that is 10 in the I direction, negative 20 in the j, positive 30 in the k. We'll have examples that will help you understand how to do all of this later. But the units of this force vector are still, for example, newtons in SI, or say pounds force in English units. Now, of course, the numbers would have to be different if we were representing the same vector, because a newton is not equal to a pound force. So let's take an example. We've got a hook here. We've got two forces, F1 and F2. F1 has magnitude 500 pounds, F2 has magnitude 800 pounds. Now it's important when you see a figure like this that's represented in a 2D plane, it indicates a three-dimensional thing. So it's important to wrap your head around it and figure out, okay, what exactly are the directions, for example, of F1 and F2? What we want to do is look at these forces and figure out the total force on the hook. So we'll have to add these together and understand we're pretending that the hook is a single point, although of course it isn't. Or you could say that the force in these ropes go through the origin, where that origin is located at the center of the hook, where the hook actually has no material. Okay, however we want to look at it. But F2, you notice that the plane for F2 is a plane that passes through the z-axis and is rotated off of the x-axis by 30 degrees. And then within that plane, F2 is angled down by 45 degrees. On the other hand, it looks to me like the force F1 is a little more simple. F1 lives or exists in the YZ plane alone. So it's not rotated about the z-axis or the y-axis, for example, at all, and has angle is shown there with a 3, 4, 5 triangle to make our lives easy as we're trying to learn and understand this. Now, there's two angles that describe F2. There's the 30-degree rotation angle of the plane that F2 exists in, and then a 45-degree angle down from the XY plane to force F2. So what will we do? Well, we'll write F1 and F2 in Cartesian form, then we'll add the two forces by adding their x, y, and z components. We should have said z here also because we're dealing with three-dimensional vectors. Now obviously F1 is only going to have a y and a z component, whereas F2 will have an x, a y, and a z component. So first of all, let's resolve F1. That's pretty straightforward. The amount of force from F1 in the horizontal direction, or the x direction I should say, is 0. The vector doesn't have any length along that direction. But Fy, the y component of F1, is, well, let's see, the y component, remember y is not pointing up now, it's pointing off and to the right. Well, then that would be 4/5 of the 500 pounds, so 400 pounds. Whereas Fz, the vertical component, would be 3/5 of the 500 pound, or in other words, 300 pounds. So if we write F1 in Cartesian form, then we'd have 0 in the I direction, 400 in the J, and 300 in the K, and of course the units are pounds. You guys know me, I will definitely keep you on your toes about units. They're very important, and you need to use them. Now, on the other hand, F2, if we want to resolve it into components, we've got to consider the fact that it's in a rotated plane, right? There's no 0 component here along any of the axes. So what we're going to do is consider an F2 prime force first and get the magnitude of F2 prime and F2z, which F2z is a valid component of it. So let's resolve it. So F2z would be the magnitude of the vector multiplied by sine of 45 degrees. And of course, it's in the negative direction. So 800 times negative sine 45 degrees, you can see there is negative 565.7 pounds. F2 prime, which is in the xy plane, however, would simply be 800 times cosine of 45 degrees, because notice it's the cosine side, since f prime is touching the 45-degree angle, or it's adjacent to the 45-degree angle. So numerically, since sine and cosine of 45 come out to the same thing, we end up with 565.7 again. But notice that f2 prime is a positive number, right? We always want to end up with it being a positive number and then figure out later whether it's actually positive or negative relative to the coordinates. Now, in this particular case, f2 prime is positive along the x-axis and positive along the y-axis as we project it onto those two axes. So we take f2 prime and we further resolve it into an x component. So remember, its magnitude was 565.7 times the cosine of 30 degrees. So that'll give us the amount of the vector that lies along the x-axis, because that direction is touching the 30-degree angle, or it's adjacent to it. And f2y would be the sine side. You can think of this f2 prime as the hypotenuse of a triangle, and all we're trying to do to get f2x is to get the base of the triangle, and f2y, we're trying to get the y component, or the vertical component of the triangle, at least in the first quadrant. Okay, so that's how we resolve F2 into its components, and then we can write it based on its I component, 489.9, its Y component, 282.8 J, and then plus its Z component, which is a negative 565.7 K, and again, the units are pounds. Now that we've got the vectors written out in Cartesian form, the resultant, or the sum of the two, is just add them together, term by term. So 0 plus 49.9 is close to 490. We've rounded it up to account for significant figures. 400 plus 282.8 would be 682.8, round that up to 683. And then 300 minus 565.7 gives us a negative 266 after rounding. So now we've got the resultant vector from that problem, which is what we wanted to know. If we wanted to, we could go ahead and calculate the magnitude of that vector. We could calculate angles to the various axes, the x, y, and z axis, and maybe that would be useful. So let's continue with our concept quiz. If you only know the direction, the unit unit vector, you can determine the blank of A uniquely. Okay, so if we know UA, it's a unit vector in the direction of A, then what can we determine about A? Could we determine the magnitude? Well, no, that's exactly what's missing from UA. Could we determine the components, AX, AY, and AZ? No, we could not, right? Because AX and AY and AZ all have to do with the magnitude of A. How about the angles alpha, beta, and gamma? Yes, we could certainly determine the angles alpha, beta, and gamma because we could resolve UA onto the x, y, and z axes because it has unit length. So it would be pretty easy. Cosine of alpha, for example, would be UA in the x direction. Okay, so it would be easy. We wouldn't even have to divide by the magnitude of UA because the magnitude is 1. And it would be similar for beta and gamma. For a force vector, the following parameters are randomly generated. The magnitude is 0.9 newtons, alpha is 30 degrees, beta is 70 degrees, and gamma is 100 degrees. What is wrong with this 3D vector? Is the magnitude too small? Not necessarily. The magnitude is 0.9 newtons. There's nothing wrong with that. The magnitude can be pretty much whatever we want it to be. The angles are too large. No, any of the angles can be between 0 and 180 degrees. All three angles are arbitrarily picked. Yeah, that might be a problem. How about all three angles are between 0 and 180? Well, no, they're supposed to be. So C would be the answer by elimination. But how would we prove that it's wrong? Well, remember, cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared should be equal to 1. And if you grab your calculator and check, you'll find that's not the case for this. So we can't, remember, alpha, beta, and gamma are dependent upon one another. Those are the angles from the vector to the various axes in the coordinate system. And they can't be just randomly generated and be correct. We might get lucky and choose values that will produce, cosine squared of the sum as 1, but I'm pretty sure this one won't. So that would be the problem. Now, this is a group problem solving. If we were in class together, I would suggest that the class go through it as groups. If you're with someone right now, you should try it. Don't just skip ahead in the slides. If you're on your own, do try to go through this and see if you can solve it on your own. But of course, you'll have the slides to go through and show you where you should come out. But don't just look through it and think, yes, I could do that. Try it, give it a shot, and then see what you come up with. So now let's consider the attention quiz. What is not true about a unit vector, for example, UA? Is it dimensionless? Well, we can get a unit vector by taking, say, a force vector and dividing it by its magnitude, both of which have units. So the units divide out, and in fact, unit vectors would be dimensionless. Its magnitude is 1. Well, that's actually why it's called a unit vector. It's unity. Its length, its magnitude is unity, or 1. So A and B are not true. They're not the answer, because those things are in fact true about unit vectors. It always points in the direction of the positive x-axis. Well, notice they've given us UA. UA is a generic unit vector, whereas something like I is a very particular unit vector that points along the positive x-axis, but U is more general. You might point along any axis or maybe no axis. Okay, so it points along the direction of the vector A, and the vector A, whatever it may be, may or may not point along the x-axis. How about it always points in the direction of vector A? Well, that's actually true. That's why it's called U sub A. So C is the one that is not true about unit vectors, at least about UA. It is true about I, but it's not true about J or K. Okay, question 2. If a force F is 10I plus 10J plus 10K newtons, and G, another force, is 20I plus 20J plus 20K newtons, then if you add those two together, what would you get? Well, you would simply add the components. So you'd take the 10 on I plus 20 on I, that's 30I, and the math is really easy. In fact, we get 30I, 30J, 30K. The only answer that matches that is option D.